Hi, I'm Nick Bonaker, and I'll be presenting a performance evaluation of Nomon, a flexible interface for noisy single-switch users. I've been working on this research with an awesome team, including Dr. Emli-Mari, Professor Keith Vertanen, and Professor Tamara Broderick. So first, some background on our target population and single-switch communication. Individuals with severe motor impairments, such as cerebral palsy or locked-in syndrome, often are completely paralyzed except for a few motor groups. They may be able to say, raise an eyebrow, breathe, or blink on command. Specialized devices called single switches can then detect these activations and relay them to a computer interface. The goal of a single switch interface is to facilitate complex interactions such as browsing a computer, composing text, or gaming, using solely a single switch input. I'll show the results of our recent user study and how Nomon, our single switch interface, can facilitate a fast and flexible computer interaction experience. RowColumn scanning is a popular interface among single-switch users. The interface allows users to select from a grid of options as it progressively scans through them in row-column order. However, there are a few limitations that arise from this method. Firstly, options must be arranged in a grid. This poses a problem for tasks that are not grid-like in nature. For example, browsing the web, choosing among files, or playing a game. Secondly, RowColumn scanning has no built-in error tolerance. Single-switch users often have a fair amount of noise in their activation times, and even just activating their switch can be arduous. Lastly, selection time does not scale well as the number of options increases. Lots of dead time can accrue as users wait to scan through long lists of options. This poses a barrier to tasks that require a large number of options, such as computer navigation or gaming. Our single-switch interface, Nomon, directly addresses these limitations through its flexible selection scheme. So Nomon works a bit differently than RowColumn scanning. It uses clocks to indicate selection options. I first find the option I want to select and look at the clock to its left. Let's put a few more clocks on the screen. Say I want to select the letter B out of these 4 options. I start by focusing on the clock to its left. I select this clock by activating my switch, or clicking, when the minute hand passes the red noon line. That will be right about now. Notice how the A and C clocks turn black. Nomon highlights its best guesses for the clock you're going for in blue. Clocks are narrowed down over multiple switch presses, or clicks, as more clocks turn black. So I'll press again when the minute hand on the B clock passes noon. When the software is confident in my desired clock, it makes the selection. In this case, the B clock is the only remaining blue clock. The number of clicks needed to make a selection can vary. The number is determined by my precision in clicking when the minute hand passes noon on my desired clock. In a keyboard application, options extend to include characters and word completions that facilitate text entry. We have a demo of our keyboard application available on our website, and we encourage you to try Nomon out. One benefit of this clock mechanism is that it allows flexibility in the layout of these options. They are not restricted to a grid as with RowColumn scanning. This flexibility makes possible certain tasks that cannot be easily placed in a grid, such as navigating a Google search page as you see here. Nomon clocks can be positioned next to every selectable option on the page, essentially making the website accessible to a single switch. Now, a few questions arise concerning Nomon's real-life performance as a single switch interface. These questions were the motivating factors behind our performance evaluation. First, what does the long-term learning curve for Nomon look like? As a more complicated interface than RowColumn scanning, how quickly can individuals learn to use Nomon effectively? More directly, given its theoretical advantages, can Nomon outperform RowColumn scanning in real-world text entry? We're also interested in how Nomon performs in applications beyond text entry, similar to the web page navigation example. And finally, having been tested with only participants who are not single-switch users, could Nomon be a feasible interface for individuals with motor impairments? To answer these questions, we conducted a multi-session user study. We followed 13 non-switch users across 10 sessions as they learned to use both Nomon and RowColumn scanning. We compared their performance in both a text entry task and a picture selection task designed to simulate uses beyond text entry. As a first step towards answering this last question, we ran a pilot trial of Nomon with an experienced single-switch user. To further address this question with our non-switch user participants, we designed and validated a method to approximate motor-impaired operation of a single switch. We wanted to ensure our methods were sound before diving into a large study involving individuals with disabilities. However, we also wanted to ensure that the data we collected was as representative of our target population as possible. Our approximation of motor-impaired switch operation is based on mimicking the reaction time distributions of actual single-switch users. We developed a noisy webcam-based switch to lower the reaction times of our participants down to levels more representative of the target population. In the top row of this graphic, you can see histograms of the reaction times of non-switch users in light blue and switch users with motor impairments in dark blue. Notice how the switch user population tends to have much longer reaction times than the non-switch user population. On the bottom row are histograms plotted on these same axes, but of the unhindered reaction times of our participants in light blue and their lowered reaction times when using our noisy switch in dark blue. Notice how our noisy switch lowers participants' reaction times down to levels that are more in line with the data we have on our target population. Now let's look at the results from the text entry task with the non-switch user participants. We found that participants were continuing to improve with Nomon up to the final session, while they stopped improving with RowColumn scanning halfway through the study. In the final 2 sessions, participants typed an average of 15% faster using Nomon. We found no difference in error rates between the interfaces, though participants had a higher click load, meaning they had to click more times per character using Nomon. The SingleSwitch user completed the same text entry style task as the non-switch user participants, and we compared their performance after an equal amount of practice with Nomon. Note that this switch user regularly uses a RowColumn scanning interface with a fast 100 millisecond scan speed. This proficiency allowed them to use Nomon at a rotation speed 4.4 times faster than the average non-switch user in our trial. The error rates of the switch user were in line with those of the non-switch users. However, the switch user typed 1.5 times faster with a 1.8 times higher click load than the non-switch users. In the final session, we asked the non-switch user participants to complete a task designed to simulate uses beyond text entry, particularly uses with a large number of unordered, uniform prior options. In order to have a direct comparison to RowColumn scanning, we were limited to placing these options in a grid layout. However, you could imagine Nomon working in a similar scenario as a web page with a comparable number of buttons and links. We found that Nomon particularly excelled in this task. Participants not only selected options 35% faster, but they did so with half as many corrections using Nomon. So to wrap up, Nomon is very much in active development, and we encourage you to try out our keyboard demo on our website. Also, come check out our live demonstration of Nomon at the Chi Interactivity demo. All of our code is available as open source on our GitHub. We see many directions for Nomon in the future, and we hope people can adapt our code and explore new applications.